Okay, now I'm going to discuss the symmetry factor for disconnected diagram. As I have mentioned many times that disconnected diagrams will have a symmetry factor of 1 over factorial n if there are n copies of a connected diagram in that. So this I'm going to demonstrate for the simplest example in the vacuum sector, which is as follows. So recall that T tilde 0, 2, which is the vacuum graph with 2 vertices, vacuum contribution with 2 vertices. It is given by 2 graphs, this plus this, as we just discussed in the previous slides. Now, if you consider T tilde 0, 4, which means the vacuum diagram, vacuum contribution with 4 vertices, the expression for that will be 1 over factorial 4 I g over factorial 3 times del over I del j cube to the power 4 times 1 over factorial 6 half, let me write in a simpler form, I over 2 j delta j to the power 6. So this is the 4 vertex contribution, g to the power 4 contribution to the vacuum vacuum part of W tilde j, and these will have disconnected. This will have disconnected diagrams and connected diagrams. This is a sum of disconnected and connected diagrams. Now, the disconnected diagram can be argued, a topological argument can be given that it is only possible, only possibility for that is this 1 over s T tilde 0 2 times T tilde 0 2. The reason is that it has the diagram has to have 4 vertices, and if it has to be disconnected, then it should be that the 4 vertices should be divided into 2 with 2 vertices each, because you cannot have a disconnect. You cannot have a vacuum graph. Both of them have to be vacuum, because vacuum graphs in both the disconnected. In the disconnected piece, both the components should be vacuum graphs, and you cannot have a vacuum graph with 1 vertex, as we discussed before. So it has to be at least minimum 2 vertices. So this is the only possibility, and diagrammatically it is given by this. We expect from our discussion before that S must be 2. We expect S must be 2, and that is why we will verify. Now, oh gosh. which is what we shall verify now. Okay, so the procedure is that identify what are the terms in T tilde 04 gives rise to T tilde 02 square. So identify terms within T tilde 04 that give rise to T tilde 02 square. So if this 1 over s T tilde 02 square is sitting in T tilde 04, then 1 over s T tilde 02 square is what should be that? So T tilde 02 square is given by half. This is T tilde 0. Let me write T tilde 02, one factor of that, delta over I delta j cube square 1 over factorial 3 I by 2 j delta j cube. So this is T tilde 02. We have studied it, we have considered that before. This is T tilde 02. It has two vertices. It has two vertices, and that makes a total of 6 derivatives, and therefore it has to have 3 propagators, because each propagator has 2 j factors. So there should be 6 altogether, 6 j factors, and therefore it should be third power from the from W0j. Now this is T tilde 02, and if you square it, then you get this. This must be sitting inside T tilde 04. So let us now compare. So that, of course, the number of derivatives and number of j matches, number of sources matches, because number of derivatives is 6 and number of j also 6, as it is here. Sorry, number of derivatives is 6 from each one, but then there is a square there, so there are 12, and similarly this one is number of j's is 12, so that is same as number of derivatives here, which is 3 times 4 12, and also number of j's is 12, which is the number of derivatives and number of j factors matches with T04, which is just simple counting, because the T02 square has 4 vertices, and it's a vacuum. All of them are, whatever we are talking about, are vacuum diagrams, and therefore they should match, and they are matching. But the numerical factors in the denominators, they wouldn't match. This ig over factorial 3 and this I over 2, they will match. Ig over factorial 3 has total power of 4. Here also ig over factorial 3 has total power of 4. Similarly, I by 2 power also will match. What will not match is the prefactors here and here, right? Because it's a different type of organization of the derivatives, vertices, and the propagators. So these are, so let us check what are the extra factors, how the factors are different from what we have here. So in this, in T tilde 4, we have 1 over factorial 4 and 1 over factorial 6. We, instead of having that, we have half and 1 over factorial 3. So multiply this by 2 times factorial 3 square. This is half square and factorial 3 square divided by factorial 4 times factorial 6. This is what we should have, factorial 4 times factorial 6, and this is what we have already this is what we had already divided by. We had written these extra factors and I am compensating by that. And however, this is not the end. So what I have done here so far is that I have taken the same t tilde 4 factors. I have written those factors. In order to write t tilde 02 square, in order to write t tilde 2 square, I have to have these factors which I have compensated here. Okay. Now I should multiply, and this is not the entire contribution. The entire contribution will have another factor sitting here. That factor is the number of ways in which this entire contribution. Look at this. Look at the configuration here. There are 4 cubic vertices applying on 6 propagators, but here only 2 cubic vertices are applying on 3 propagators, and then you are taking square of that. That's a different configuration. So the question is that, of course, this is hidden in this. There are many possibilities of doing this, applying these operators on these j's, and some of the possibilities will produce this type of configurations. Question is that what is the number in which there will be many terms will give the same contribution, that number, the repetition that we keep talking about. So the number of repetitions, how many times will this configuration arise in this? This will have many other configurations which are all connected graphs, but this is we have identified the configurations for the disconnected piece. Question is that how many times will it arise when we do the entire calculation here? That is the question, and let me call that number as Q. So the number Q is the number of ways t tilde 02 configuration number of ways t tilde 2 configuration is repeated within t tilde 04. I explained what I meant. So that is the number that we need to calculate. And then if this is the result, then of course this expression is t tilde 02 square, and therefore this entire factor is s, 1 over s, right? So then it means 1 over s is equal to 2 times factorial 3 square divided by factorial 4 times factorial 6 times q. So if we can calculate q, then we'll be done. So that's what we do now. Calculate q. Look at the the configurations that I referred to. I'm now going into the details of that configuration and exactly how this is happening. The configurations that you see in t tilde 4 versus the configuration that you see in t tilde 2 square, right? That is what you one needs to compare. So t tilde 04 has this vertex. There are 4 of them, and there are six, they're acting on six propagators. So 4 vertices and 6 propagators. This is the configurations that you see, and there are many ways that this is happening. All these things have to be, these links have to be connected and to form the diagrams. And the configuration that we see on the other side, that is t tilde 0 2 square, is I have two vertices applying on 3 propagators. Okay, that is t tilde 0 2 vertices applying on 3 propagators, and square of that. So you just take the square of it. So this is the configurations that we are looking for, but we initially we have this, and we have to figure out in how many ways this can lead to these configurations. Okay, and the answer is that answer is that Q must be given by 2 times Q4 to Q6 2. Let me explain the notations. So I am using a notation where Q n k is the number of ways n identical objects can be divided into k indistinguishable groups. So number of ways in identical objects can be divided into k indistinguishable groups. If there are k groups and they should be indistinguishable, that means they should have same number of elements, and n objects can be divided into k equal parts only if n over k is an integer. So n is an integer multiple of k. So let me call it n equals qk. N should be equal to q times k, so that in each group, subgroup you have q elements, such that q is in integer. Right. So this is so let's see how that is happening. Why this is the formula. This should be the formula for q. The reason is that what we are doing here to get this configuration, what you have to do is we have started out, we have been given 4 vertices, and we are separating them into 2 groups of each having 2 vertices. So that is exactly what I'm doing here. We start out with n objects. These are all identical vertices, and we are separating them into 2 identical subgroups, each having 2. So q is 2 here. Similarly, we have to start with 6 propagators, and we are dividing into 2 groups. Here q should be 3, and these 2 groups are identical. Yeah, I am dividing 6 identical objects into 2 groups, each having 3 identical objects, and these 2 groups are also identical. Yeah, these are not distinguished, because the reason is that if you suppose I take an example. First I make them distinguishable, 1 2 3 4, and then I take a combination 1 2 3 4. Now this is same as 3 4 1 2, because it's just a derivative. They are all indistinguishable, and these 2 factors are also indistinguishable. They just give some mathematical expression. It's just a square of that, right? So therefore these subgroups are indistinguishable. So how many ways you can do that? You can take 4 objects and divide it into two groups, each having 2 elements. Similarly, 6 objects divided into 2 groups, each having 3 elements. Now that after you subgroup, after you create these subgroups for both the vertices and the propagators, the question is that now you have to answer the question, which subgroup of vertices should be associated to which subgroup of propagators. So I have already associated them. So just imagine not having this, not having this. You have only this one group of 2 vertices and the other group of 2 vertices. Similarly, one group of 3 propagators and the other second group of 3 propagators, right? So now you have to associate. So it is like, if this subgroup of vertices is 1 and this is 2 and the propagator subgroup is A and B, you have 1, 2, you have to associate it with A, B. Now 1 can go to A, 2 can go to B, or 1 can go to B and 2 can go to A. Both of them will give the same answer. So there are 2 possibilities. When you associate at the level of associating the vertices with the subgroup of propagators, there are 2 possibilities, and that is why this factor of 2 is here. So once you fix, so let me color code it. Once you fix the subgroup of vertices, is associating them with the propagators can have to. There are so you can switch between this. So there is an interchange symmetry between the 2 groups of them. So that is this factor of 2. So this is basically number of ways to associate derivative and propagator subgroups. Okay, so that is the formula. Now let us calculate Q and K. How can we calculate Q and K? Now to calculate Q and K, proceed in the following manner. So calculate Q and K. So define Pn sub n1 to nk to be the number of ways in identical objects can be divided into k distinguishable groups of n1 to nk number of objects. It's like partitioning. So you have n objects and you are partitioning n objects into k subgroups. These k subgroups are indistinguishable. Original n number of particles are indistinguishable, but the k subgroups are distinguishable. So n1 sum over I ni is equal to n, of course. Let me write then. Sum over I ni is equal to n. So I take n and divide it into k subgroups, distinguishable subgroups. Then this is a standard result, or you can try to argue why this result is right. This is given by factorial n divided by factorial n1, factorial n2, up to factorial nk. Okay. That's a result that is known, and I'm borrowing that known result here. Now, if n1 equals n2, if all these nks are ni's are same, is equal to q, all these k in ni's are same, then p in q comma all of them are q will be factorial n divided by factorial q to the power k, because all these n1 n2 factorials are all q factorials. Okay, now all your, since when all these individual numbers n1 n2 up to nk are same, then only you can have an option of making the subgroups indistinguishable. So these are the result for the distinguishable subgroups, each having equal number of elements, which are q elements, equal number of elements, which is q. Then from there, if given this result, then in k, basically when you have all these k subgroups to be indistinguishable, you will simply have factorial n divided by factorial q to the power k times factorial k, because now these k groups are indistinguishable. So you divide by factorial k. So this factor comes because k subgroups are indistinguishable. Then you just directly calculate the result. You'll have this result here. So q in our this thing is 2 times q4 2 is given by factorial 4 by, so q is 2, k is also 2, because yeah, two groups each having 2 elements. So this is q square times 2 square times 2, so 2 to the power 3 times q 6 2 will be factorial 6 divided by this is q is 3 factorial, and k is 2 times 2. This is the result, and therefore 1 over s, which we had here, times 2 factorial 4 over 2 cube times q. So I'm writing q factorial 6 divided by factorial 3 square times 2. So factorial 6 cancel, factorial 4 cancel, factorial 3 square cancel. Then you have 2 square times 2 to the power 3. These are divided by 2 to the power 3 times 2. So the result is half, which is what we expect. So that is the proof of the result. But yeah, so now one can generalize. I mean, the generalization will be similar to this argument, which I'm not going to do. Yeah, so this is the end of